Okay, thank you very much for the introduction and for the opportunity to exchange with you. I'm very glad to join the lab and your team for my new postdoc. So I have prepared a presentation which is a summary of my thesis and postdoc work. So done the Berquin Laboratory and the Observatory of Lyon. And the topic of my presentation is about the detection, the characterization and reconstruction of objects from thin signals in images with double applications in astronomy for direct imaging and in microscopy. So let's start with a few words about the context. So our goals are triple, since we want to detect, to characterize and reconstruct objects, which means that we want to localize this object to estimate their physical properties, and also to build faithful images, to reconstruct faithful images of objects having a complex shape. And for these three tasks, we are working with a series of images in which the signal of the object of interest is corrupted by a strong noise. So this problem is very general and encountered in several application fields, different scales, from microscopy to astronomy through biomedical imaging or remote sensing. So I have worked on two of these fields, and I'm going to present you today some of the method we have developed. So to continue, I would like to introduce briefly these two fields, and of course, you are very familiar with this one, direct imaging for the detection of exoplanets. So let me just to recall that from a signal processing point of view, the primary goal is to unmix the very faint signals from the exoplanets and the very strong signals from the host star. So I have worked on, and I'm still working on the data recorded by the SPHERE instruments operating at the VLT. And we have series of images at high contrast and high angular resolution. But as you know, the detection remains challenging from this series of images. So signal processing is one of the key steps, such as the key step of the process to perform the detection. So I would like to illustrate this need of signal processing by showing you or re-showing you a typical sequence of data. So you have here some examples. So this is a time series from the SPHERE instrument, from the IRDIS imager more precisely. The star is at the center, and we have represented by the two red circles the locations of two non-point source objects. And we have on the right spatial temporal slice cuts along the black straights and dashed lines. So I'm going to show you some frames. So let's go. I'm playing the sequence of data. So based on these examples, we can have several observations. The first one is about the signal of the exoplanet. Of course, it is very faint, and it follows an apparent motion, a rotation, since the acquisition are conducted using the pupil tracking mode of the telescopes. And concerning the background now, that is to say the nuisance components, the residual signal of the star, it is non-stationary and spatially correlated, as shown by the slice cuts. And we have also sometimes some strong fluctuations due to bad observing conditions, for instance. So this kind of events are rare, but they can occur sometimes. And we can also we have also access to multi-spectral data on a small area centered near the star by using the integral field spectrographs of the SPHERE instrument. So this is exactly the same kind of data after interpolation of the recorded spectrums, and we have cubes, temporal cubes for different wavelengths. So this is our 4th point on which we based our method for the processing. So now let me to introduce the other topic in microscopy. So there are also several observational techniques to image microscopic samples, as you know. And the one I have considered is very simple, since it consists to directly put the object we want to analyze in a coherent light path, so between a laser source and the sensor. And we have the possibility to produce a multispectral data too with this kind of setup. And we record on the sensor a magnified view and an out of focus view of the samples. That is to say, the diffraction patterns or the hologram produced by the object of interest. And the goal is also to analyze this kind of data to retrieve properties about the object of interest. And you have here a typical temporal series recorded by this kind of setup. So the object of interest is just here. So this is a bead of latex in suspension in water following a Brownian motion. And so based on this example, we can have exactly the same conclusions and for direct imaging from a signal processing point of view, since the signal of the object of interest is relatively weak. The background, due to the nuisance components, is non-stationary and spatially correlated. We have also some forms of outliers in the data pointed by the red arrows due to unwanted objects such as dust passing through the light path during the observations. And we have also the possibility to record multispectral data. So we have exactly the same conclusion, and here we have a summary. So for the two problems, I'm working with multivariate data. More precisely, they have a spatial, a temporal, and a spectral diversity. And they are also impacted by some kind of outliers. And the primary goals are to extract the kind of results we have on the right, that is to say, to produce detection results, to detect the faint signature of objects, of point-like objects from the data, and also to characterize them, that is to say, to retrieve physical properties. So in the case of exoplanet detection, this is done via the spectral energy distribution of the exoplanets. And for the microscopic samples, it can be the size, the refractive index of the samples, for instance. And we are also interested in reconstructing objects having a complex shape, such as the ones of the circumstellar environment from the same kind of data. So for this purpose, I have worked on the development of signal and image processing methods for these two fields. And the methods on which I have worked are based on the common methodological guidelines following 3 points. First, the first point is about the modeling of the background, and more precisely, the non-stationary fluctuations that we have observed. We have also proposed some strategies to deal with the presence of outliers, such as the ones we have observed, and also dedicated strategies to deal with the specificities of multispectral data. So in this presentation, I'm going to give a particular focus on direct imaging, and I will give also some points and some illustrations related to holography, microscopic holography. So here we have the outline of my presentation. I'm going to present first the general methodology we have proposed from a signal processing point of view, and then the application of this common methodology to the two problems in direct imaging and holographic microscopy. So let's start with the methodology, and I would like to stress 2 points. The first one is about the modeling of the spatial correlations of the background, and also, second point, to the way to derive a robust modeling of these fluctuations of the data. So let's start with the first one, the modeling of the spatial correlations in the data. So for the purpose of illustration, I'm taking here the context of object detection, but this is exactly the same for object characterization and reconstruction for the different sub-problems that we are addressing. So as you know, the classical approach to detect a pattern is a well-known matched filter, which consists in performing a correlation between the data we have impacted by a noise and the pattern to detect, which is noise-free. So it's very simple. It works both for point-like sources, such as exoplanets, and also for spatially extended patterns, such as the holographic signatures of microscopic samples, for instance. So it's very simple, but it does not account for the spatial correlations of the data, such as the ones we have observed. So the final strategy consists in estimating from the data a whitening filter, and to whiten both the data and the pattern to detect before computing the correlations. So it's also very simple, adapted to the different spatial extent of the pattern to detect, but it does not account for the non-stationarities, since the whitening filters is global, estimated on the whole images, which means that we are lacking of locality. So let's see from the signal processing literature how we can address this need of modeling of the correlations at a local scale. So there are plenty of work on this topic, and one of the most successful approaches to do this are based on patches. So they consist in analyzing the images we have on subport of the images, that is to say on a sub window or patches of a few tens of pixels, to derive the local behavior of the images. And for instance, these two algorithms that are listed here proved to be very efficient in the context of image denoising. And they are based on the analysis of the textures and the structures of the images at a local scale of the patch. And we have here an experimental series of images recorded by a microscopic sample and some patches extracted from this series, and we can see the different structures and textures encoded in these different patches. So we based our method on this kind of approaches, and we also conduct a multivariate Gaussian modeling inside these patches through the estimation of covariance matrices to encode for the textures and structures. So here we have the framework we have proposed. So we split the images we have in small patches, and we build a different whitening filter for each patch before combining them for producing, for instance, a detection map. And we follow this general methodology both for exoplanet detection with point-like source, but also for holographic microscopy, where we have spatially extended patterns. So such a framework raises some questions, such as the way to estimate this local whitening filters and the way to adapt to the different kinds of signals we have, for instance, point-like signals and spatially extended signals. So now let's see how we can address the robustness of this model against the presence of large fluctuations, and more generally against the presence of outliers in the data. So it can be large fluctuations or defective pixels, for instance. So same things in the signal and image processing literature. There is several avenues to address this problem. And one of the first category of methods are based on the iteratively related least squares, which consists in replacing a quadratic loss when we are solving an optimization problem by another loss with a reduced penalization of the large deviations between the model and the data, that is to say, the outliers. A closely related approach is based on the use of non-Gaussian modeling. And for instance, Gaussian scale mixture modeling I will give more details about this kind of modeling in the rest of my presentations, is widely used in radar imaging to encode for the presence of cluster of clutter or spikes in the clutter of the images. That is to say, too large deviations, too large fluctuations, and they encompass the modeling of the detailed distributions of the data, and they account for the presence of large fluctuations. So now we have the different ingredients, and let's see how we can combine these different ingredients in the context of the two problems. And let's start with the first one, in direct imaging, and first in the context of exoplanet detections. So the algorithms we have proposed is named PACO for patch covariances, since it learns locally at the scale of a patch covariance matrices encoding for the structures and textures of the images. So to illustrate its principle, we have on the right a schematic representation of the data, temporal series, with an exoplanet in blue, following a rotation along time. And for each location of this putative exoplanets, we have a green patches centered on the exoplanet location, which can be computed. The exoplanet location is predicted since we know the parallactic angles during the sequence. So it's possible to extract for each position of this exoplanet a collection of patches on red on the screen that contains almost background contribution due to the rotation of the exoplanets along time. So we use this collection of almost pure background contribution to build a statistical modeling of the background at a local scale. And we then embed the statistical modeling both in the detection framework and inside a characterization frameworks. And it can be also integrated in a reconstruction frameworks for the analysis of data containing circumstellar disks. And I will derive the different ingredients in the rest of my presentations. So here we have the statistical framework for exoplanet detection. So we model an observed intensity patch R extracted at pixel n and time t at the combination between the background component f at same time and same position plus the expected signature of an exoplanet taking the form of the off-axis PSF multiplied by a certain intensity alpha, that is to say the flux of the exoplanet at a given wavelength, with f much greater than alpha h and f that fluctuates over time. So you see the nuisance component, background, the noise more generally. And we then compare this observed intensity patch to two hypotheses. Under the H0 hypothesis, this is only background, while under the H1 hypothesis, this is the combination between the background and the expected signature of an exoplanet. And we then compare the likelihood of the two hypotheses to form, and we form the ratio between the two likelihoods to decide in favor of the presence or absence of an exoplanet. And in fact, the flux alpha of the exoplanet is unknown, so we replace it by its estimates in the maximum likelihood sense to form the so-called generalized likelihood ratio test, which is the most powerful detection test for binary hypotheses. That is to say, when we are building a statistical method following this scheme. So now to continue and to derive an expression, a closed form expression of this detection criterion, we need to specify the statistical modeling. That is to say, the expression or the expression of the statistical modeling of f. So as discussed in the previous section, we have chosen a Gaussian scale mixture model, GSM, which means that a pure background patch f, still at location n and time t, is modeled by a mean that is to say encoding for the mean fluctuations along the time series, plus a random variable following a Gaussian law with zero mean, since the mean is encoded in M, and a covariance C. And the covariance is also scaled by a parameter sigma. The parameter sigma is the only difference between a classical multivariate Gaussian model and a GSM model. And both parameters, the mean, the scaling factor, and the covariance, are estimated locally at a scale of a patch, indexes by the location n in the field of view. And model patches extracted at different times at independent GSM model. We have here the closed form expressions of the different estimators, so the mean, the covariance, the scaling factors. And I would like to stress 2 points. And the first one is about the estimation of the covariance. Since in fact, the estimation of the covariance is tricky since we have only a finite set of samples to estimate it. The number of samples available, in fact, corresponds to the number of dates in the temporal series. So the covariance can be very noisy and wrong deficient. For instance, if we have less times temporal frames than the dimension of the covariance. So since this is the key ingredients of the method, a form of regularization should to be enforced. So we have studied different strategies and selected the shrinkage approach, which consists in combining different operators, different estimators, sorry, of the covariance having complementary properties. So the covariance derived directly from the data, that is to say the sample covariance, is very noisy, that is to say with a large variance, but it is unbiased since it comes from the data. And if we build for the other estimator, a diagonal matrix with the pixel variances on the diagonal, we have a low variance matrix since we have reduced the number of degree of freedoms, but it is biased. So by tuning the rho factor between the two estimators, we obtain a final estimate of the covariance obeying a bias-variance trade-off. And the important point is that the rho factor in the convex combination, in these convex combinations, is estimated in a data-driven fashion. We have here its closed form expressions, which is an extension of this work in the case of our estimators, and it depends only on the data, and it can be computed locally. It depends on location n in the field of view, which means that it adapts locally to the non-stationarities of the data. The second point I would like to stress is about the scaling factor sigma of the GSM model. So to illustrate its importance, I'm representing here some frames, data frames, temporal frames on the left, and the corresponding 1/sigma square weights. And we observe that when we have fluctuations, large fluctuations, due to pseudo degradation of the observing coordination, for instance, the corresponding 1/sigma squares are very low, thus giving a very small statistical weight to the patches impacted by this kind of fluctuations at some times. So we improve the robustness of the method by accounting for this local weight in the process. So we have specified a model, but we may wonder if it is really relevant to capture the fluctuations of the data. So we have performed several tests, and I'm representing here the empirical distribution of the residuals. So we have on the left the data that are simply centered for the mean, the estimated mean. So this is the most simple residuals we can have. So we have the empirical distributions in blue and a Gaussian fit, a Gaussian law with zero mean and unit variance in red. At the middle, this is the same kind of residuals, but that are whitened for the covariance in a Gaussian model. And on the right, this is the same things, but for a GSM model, which accounts for the additional 1/sigma² weight. So this is the only difference between the GSM and the Gaussian model. So we observe that when we are far from the star, that is to say, in an area where we do not experience large fluctuations, the noise is almost Gaussian and white, both the Gaussian model and the GSM models are able to capture the fluctuations we have in the data. But if we repeat exactly the same experiment near the star, only the GSM model is able to capture the fluctuations of the data, in the sense that the empirical distribution of the residuals in the data is close to the expected distributions after whitening for the correlations after after applying a weight on the different temporal frames. So it justifies the use of our statistical modeling. So now we have all the different ingredients: the statistical framework, the way to conduct the detection via the hypothesis test, and the model for the background, the GSM model. So we can combine the different ingredients to derive the detection criterions, which can be interpreted as a signal-to-noise ratio of detection. And it should follow, in the absence of exoplanets, a Gaussian law with zero mean and unit variance. And now it can be evaluated at each point of the field of view. And I'm representing here a map of this detection criterion obtained on real data in the absence of exoplanets. And we have in black its empirical distributions, which follows, in this case, very closely the expected distributions. And in fact, we have in practice some slight discrepancy due to the observing conditions. Since in this example, the observing conditions were especially good, but we have a kind of control of the distributions of the detection criterions, which means that we can detect sources at a controlled probability of false alarms and a controlled probability of detections. And we can also combine the two, detection and false alarms, to control the so-called false discovery rate, that is to say the number of false alarms among the total number of detections. So I'm representing here some results. So the PACO detection map on the right, comparatively to two baseline. So these methods are used classically, routinely, I would say, in direct imaging to detect point sources. There is also plenty of other methods, more elaborate than these two ones. But for the purpose of illustrations, I'm comparing on these slides with these two baselines. So we observe that the PACO detection map is very stationary, which allows to detect the sources clearly with the better detection confidence, and it also avoids some evident false detections in the field of view due to the modeling of the spatial covariances that are accounted for. Here, this is another kind of results, another real data containing two real sources, plus we have also added 30 fake sources to have more diversity. And the main message is that the detection map is smooth. We avoid some kind of large fluctuations and some kind of leakages in the detection maps due to a mismodeling of this kind of fluctuations in the data that can occur with this kind of baseline. So the detection maps are smooth, and the detections can be done at a controlled probability of false alarms, almost. So once the detection has been performed, we can characterize the detected sources, that is to say, in terms of astrometry and photometry. So we refine these two quantities using exactly the same statistical framework, but at a subpixel level. And since we have estimators for these two quantities, unbiased estimators, and a model, we can compute for each one confidence intervals using the Cramer-Rowell bounds. That is to say, the standard deviations or the variance about these two estimators. And we can conduct such a task at each point of the field of view. So we have this kind of information about the astrometry and photometry confidence. And we can also compute at each point of the field of view the contrast, that is to say, the minimum flux that an exoplanet should have to be detected by an algorithm at a given probability of false alarm and probability of detection. And we observe that some areas are less favorable than other for the detection, which can explain the difficulties of other methods in this kind of areas, presenting several false detections. And I'm reminding you that only the probability of detections is lowered in this kind of areas with SPACO. The probability of false alarms is controlled. That is to say, false alarms are not expected here. So beyond the detection of exoplanets behaving as point-like sources, we are also interested in reconstructing objects having a complex shape, such as the ones of the circumstellar environments. So we have proposed to embed the statistical modeling I have presented based on the GSM model in a reconstruction framework. So this is the same kind of model for the data, which means that the intensity R are still modeled by the combination between the background component and the component of the star object transformed by an operator A. And this operator A accounts for the different instrumental effects, that is to say, the rotations of the object along time, the attenuation by the coronagraph, and the convolution by the off-axis PSF. And we obtain an estimation of the object of interest, that is to say, an image of the flux distribution of the disks by solving an inverse problem, in which the minimized objective function is the combination of two terms, a data fidelity one that depends explicitly on omega. Omega is the statistics of the background estimated locally via the GSM model. And we have also a regularization term to enforce some priors on the object of interest, such as sparsity, since we are expected to reconstruct a bright disk on an almost null background, and smoothness and edge-preserving constraints also. So here we have details of the different terms. So the data fidelity one is here. So as I have just said, the model of the background is exactly the same, a mean plus a random variable scaled by a parameter sigma, and this random variable followed a covariance C. And all the parameters are estimated locally. And under this model, the data fidelity terms take the form of colloquial forms in which we minimize the residuals. The residuals are the data minus the estimated mean minus the estimated current contributions of the south objects. So this is exactly the same kind of estimators, but I would like to stress that these estimators depends explicitly on the contribution of the objects. That is to say, the mean depends on the south object X that we are looking for. The same thing for the covariance and so on. And we need to perform a joint estimations of the different terms. On the one hand, background of the noise, of the contribution of the noise, and object of interest, since a bias can occur. This is a well-known self-subtraction effect in direct imaging, since, for instance, a part of the object of interest can be encoded in the mean, and then the mean is removed. So we perform a joint estimations of the different quantities, background statistics, and object of interest to bypass this effect. So this is the frame, the detailed explanation here, but I can skip it. And the second term of the problem, which is important, is the regularization one, which promote some constraints, some priors on the object of interest. And we are looking for sparse objects on your almost pure background, and also for smooth objects with sharp edges. And the key point of the method is that the different hyperparameters, the different tuning parameters, here this is the parameters giving the weights of the relative the relative weight of the different terms. All the hyperparameters are estimated in a data-driven fashion from the data. So by minimizing a quantitative criterion. So we have a criterion which is minimized, and it gives an estimate of the different hyperparameters. And the minimized criterions, this is the sure estimates, which is an estimate of the mean square error, which can be computed only in the case we have the ground truth. Here we don't have the ground truth, so we have an estimator of the mean square error, which is a kind of proxy of this error. And then we have all the ingredients, the data fidelity terms that depends on the statistics of the background, and the regularization terms that depends on some hyperparameters estimated directly from the data, so we can solve the optimization problem. So I'm going to show you some results now obtained on different well-known stars hosting circumstellar disk with various morphologies. So the proposed method is at the bottom, comparatively to one baseline used classically in direct imaging. So we can observe that the proposed method avoids some stellar leakages, especially near the star, due to the modeling of the fluctuations of the data. And it also avoids evident artifacts, such as discontinuities in the disk structures, since we account now for the instrumental effects, and we perform jointly the estimation of the background statistic and of the object of interest to avoid self-subtraction. And since we have a model of the instrumental effect that depends explicitly from the convolutions introduced by the off-axis PSF, we can also produce unblurred, deconvolved images of the object of interest. So now I'm going to switch to the processing of multispectral data. That is to say, we have proposed to extend our method in the case of multispectral data, such as the one recorded by the integral field spectrograph of SPHERE. So this is the same kind of data, but the goal is to process now jointly all the spectral channels to improve the diversity of the data and to improve the unmixing of the different components. So the first step is to align the speckles, to have exactly the same speckles at the different times and the different wavelengths, since the method is based on the statistical modeling of the speckles at a local scale. So now let's see how an object of interest is moving along this kind of data. So along the temporal series, this is still a rotation. And now along the spectral axis, this is a translation due to the magnification of the speckles. And the algorithms account for the specific motion of the source to unmix the different components. We have increased the diversity by the spectral diversity. And concerning the statistical modeling of the nuisance component, we still encode for the spatial correlations, but also for the spectral correlations of the data that are combined in the model of the statistical model of the background. Sorry. So now I'm going to show you some results. So this is the same kind of slide with only baseline that are used routinely in direct imaging. But the key message is that the map produced by the proposed method are relatively smooth, which make easier the detection of point sources at an almost controlled probability of false alarm. In fact, we can have a discrepancy, but we avoid some leakages in the field of view. And we can also estimate the spectral energy distribution of the detected sources with confidence intervals for each one, reliable confidence intervals. We have tested it in simulations, and same kind of results. We can same kind of process. We can extend the method in the case of the reconstruction of circumstellar environments. So this is here results obtained on the data of the IFS instruments in the presence of circumstellar disk. So we have the proposed method at the bottom comparatively to the baseline. And same observation than in ADI. We avoid stellar leakages near the star and some evident artifacts such as discontinuities in the disk due to the self-subtraction phenomenon, since we now account for both the statistical modeling of the background and instrumental effects. So now I'm going to show you just some illustrations of the extension of this kind of methods in the context of holography, microscopic holography. So basically, the main difference between direct imaging and holography from a signal processing point of view is related to the spatial extent of the pattern to detect. Point sources for exoplanets and a spatially extended pattern for diffraction diffraction pattern. So now it means that the detection criterion should be evaluated for each fraction of the pattern of interest, which is non-null. So the computational the computational cost of this kind of method can be very high, since we need to repeat this process for every pixel of the field of view and for every frame and so on. So we have proposed some approaches based on dictionary learning and on dictionary learning and so on to improve the scalability of the method. And I'm going to show you here a slide of results. So you have here the temporal frames recorded in digital holography. We have here the location of a known pattern, very faint, so we cannot see the pattern by visual inspection. And we have here the detection map obtained. At the left, this is a baseline that ignores the spatial correlations, that accounts only for the variances of the data. At the middle, this is the proposed method, and we have obtained the result using a small square patches, which means that we are estimating the covariances on the area of these square patches, that is to say, very locally. And we have studied several tessellation strategies and observed that if we choose patches with holes, we further improve the results, since we are now able to capture correlations that are at a longer scale. And between these results and these results, the only difference is related to the spatial extent of the patches. And the number of active pixels in the patch is exactly the same, which means that we have exactly the same size of the covariance matrices, since we have still a finite set of frames, of temporal frames, to conduct the estimation of the covariance. So we need to preserve the size of the covariance, but now the covariance is estimated less locally. And here we have another kind of illustration of the extent of results, now in the context of object reconstruction. So the goal is to reconstruct images of holograms impacted by the diffraction effect. So we record this kind of holograms, and the goal is to obtain this kind of results. And we have proposed some methods to perform jointly the reconstruction of the object of interest with the estimations of a non-experimental parameters. For instance, in this kind of setup, there are a lot of parameters that are not precisely known, such as the central wavelengths of the laser jet that can evolve during times, or the specificities of the CMOS sensor. So we perform jointly the estimation of the instrumental parameters and the reconstruction task, and it improves the spatial resolution. So to sum up, we have considered two problems different fields. For both one, we have multivariate data, more precisely data with a spatial, temporal, and spectral diversity, which can be impacted by some outliers in the field of view. And we have proposed method to detect the faint signatures of the subject of interest, and also to characterize this object, and also to reconstruct objects having a complex shape, such as circumstellar disk in astronomy, and also samples, microscopic samples of a complex shape, for instance. In the case of circumstellar disk, I have the void to mention that we are also able to mix the contribution of the extended sources, the disk, and the contribution of candidate point-like sources by combining Rex PACO designed for disk and PACO designed for point sources. And for these different tasks, we have based our methods on 3 points. The first point is about the modeling of the fluctuations of the noise, of the nuisance components. The second point is about the modeling of the large fluctuations using robust approaches. And we have also proposed multispectral extensions to deal with the specificities of this kind of data, such as the ones produced by the IFS. So I would like also to mention that the different algorithms are almost unsupervised, since when it's possible, we try to estimate the different parameters, the hyperparameters directly from the data. This is the case for the shrinkage of the covariance. I have presented it in the second section. We have also strategies to smooth the estimated spectra of the exoplanets according to the level of the noise, for instance. And I'm giving here to finish my presentation some open research directions. So there are several avenues to improve this work. And in the context of direct imaging, the goal is to improve the detection sensitivity, the accuracy of the characterization, and the faithfulness of the reconstructions. And the point I would like to investigate in the context of my postdoc starting with you is to build more complex and finer models of the observations by taking benefit, for instance, from the large data volumes that are available. For the SPHERE case, we have 5-year operations of the instruments. And I would like to combine this the machine learning approaches that can be derived from this large volume of data with statistics and physics-based modeling. Statistics-based modeling about the nuisance components and physics-based modeling about the instrumental effects, for instance. And by combining the two, we are hoping for a trade-off between the advantages of the two approaches. That is to say, the generalization capacity of learning-based approaches and the well-controlled framework of statistics and physics-based modeling. So I'm thanking you for your attention, and I will be happy to answer questions you may have.
Thanks a lot, Olivier. That was very clear and very interesting. I have a few questions, but maybe I don't know if someone else has some. We can. Oh, I'll take the first one, and then you can come after. You show results compared to T-Loki and CLIP that is currently. That have been definitely used a lot recently in our community. But I was also interested if you had like some ideas of comparison with other more recent methods, such as the match filter, forward model match filter, for example, that has been published by review a few years ago. So I would imagine, because of the way that the match filter is done, PACO is at the minimum a lot faster But do you see other advantages of your method compared to
yeah, yeah. So I see the point. Thank you for the question. So in fact, the comparison of the different methods is very difficult. In fact, since we need to process exactly the same kind of data set in the same condition and so on. Some algorithms have hand tuning parameters. So I don't want to speak about the comparison between the two algorithms now, since I'm not the best person to do this, I think. But yes, indeed, there is, in my point of view, a need for comparing the different methods, and I think that the initiative of the blind test last December was great in this sense. But yes, there is several points in terms of comparisons. In my point of view, more than the computation time, the most important point will be, in my point of view, the capacity to detect faint objects, and assessing this point is really difficult using blind tests, since classically we give exactly the same score to a method able to detect round bright planets, and a method able to detect a more fainter planet. So yes, there is plenty of work to do on this point to obtain comparisons between the different methods. But in my point of view, all the methods have their drawbacks and advantages in some regimes, especially in observational regimes. So it will be interesting to see which method best fits some kind of regimes.
Okay. So yeah, I have other question about disks, but it's maybe more technical, so we'll talk about it tomorrow if you want. Is there other questions, or I have others.
I had one question that I asked. We discussed a bit with Maud. Did you check whether it's better when you have open loops? Is it better to remove the frames? Yeah, or using your GSM?
Yes. So my answer is double. In fact, yes, the point is that this is a weighting of the different temporal frames. So if the abnormality becomes the normality, for instance, I have seen some series of images in the sphere instrument when we have more than 30 or 50 images with this kind of results. So in this kind of framework, the abnormality becomes the normality, and the process fails. But if we have only one, in my point of view, if some part of the spectral field remains exploitable, so maybe not in the case of an open loop, but in the case of low wind effect, for instance, yes, it is preferable to keep the frames. But in the case of open loop, no, since all the frames is bad, since the goal of the process is to give different statistical weight to the different points of the field of view at different way at different times. So there is no gain to keep a frame in open loop, but there is a gain to keep a frame impacted only on small areas, on some areas by large fluctuations.
Thank you.
I had also a question. Have you tested your this algorithm with other chronographic instrument than SPHERE? Because we've noticed also with time that there is differences mainly between space and ground, because the PSF is a lot more stable in space, for example, but also even between bands. For example, if you go to larger wavelengths, you tend
So this is
to have a lot more stable PSF, and sometimes some algorithms don't work as good changing instruments.
Yeah, sure. So yes, I've tested it on NACO data on several targets, beta peak, PDS70, HR 8799, and so on. So we have the same statistical guarantees in terms of control of probability of false alarm and false detection. I have also tested it recently on some GPI data, but not too much test, just a few data sets. And the results are the conclusions are almost the same in the sense that we can control, of course, the probability of false alarms. Maybe we need to refine. We have a parameter which cannot be estimated, in fact, in the method, and it depends only on the instrument. So for the CI instrument, this parameters is fixed since it is related to the expected size of correlations in the data. So I don't perform a refinement of these parameters. So it will be a possibility to refine the results on the GPI data using these parameters. And concerning the wavelengths, I have tested it in the context of direct imaging on other instruments such as KEK and another one, the LBT, where the spectral wavelengths, the considered band is higher. I don't remember the exact band, but higher than 2.3 micrometers, something like this. And in fact, in this kind of band, the off-axis PSF, the instrumental PSF, is spatially extended on a large field of view, more than for the SPHERE instrument in H2, H3, or K1, K2, for instance. So it means that we need to choose a large patch size to encompass the core of the off-axis PSF. And if we do this, if we choose a large patch size, we have a problem for the estimations, since we have a covariance matrix with a very high number of degrees of freedoms, and we have only a finite set of samples to perform the estimations. So in this case, when the spectral band is high, the results are worse than for the SPHERE instrument, for instance. Of course, yes.
Okay. Oh yeah, this is very interesting because it's kind of counterintuitive, because with higher bands, usually the PSF is more stable.
Yeah.
So people would expect that it's easier. But
in fact, this is a problem directly related to the estimation, to the estimation statistics in a statistic point of view. So yes, the data are better, but the statistical modeling is worse, in fact. Yeah.
Okay.